Here you can see, since we are now involved with the third layer from bottom, or the network layer, at the client side, at Alice place, data will come down from the application. Say she is using a mailing application. Yes, is trying to use a mailing application. It will start, data will start, a message will start from the application layer. It will go down and encapsulated as a datagram into the transport layer as a segment or datagram. From there it will come to the network layer, and here we are interested in the network layer onwards. So from network layer we know what it does. It mainly does packetization, dividing the data into some sized packets, some fixed size packets. And next it will also do addressing, in the sense it will add the source address and destination address, and finally it will also do the routing. It will decide where it has to go, in the sense if the packet has to reach Bob from Sky Research Labs Alice, what is the path to be taken? Here we have shown a brief example of the internet, where it will have different types of networks. In the sense, it will have LANs, it will have point-to-point WAN, it will have switched WANs as we showed here, another point-to-point WAN, and then a LAN in scientific books. So this is our destination. So it should, what should this network layer do? Please remember the tasks of the network layer. First one is packetization, dividing the data into some nominal size packets. Then addressing, adding the source and destination address, IP address, 32-bit IP address. And then third one is routing. It should find the correct path for the data to flow from Alice to Bob. So we can see here, as in the client site where Alice is there, she is the sender. From the application layer, data starts flowing to the bottommost physical layer, and in the network layer, it will decide that the next hop, the next point where data should go is router R2. It will get to know that it is connected to router R2, and it will forward the packet there. So R2, again, see, just look at this. R2 has two sets of physical and data link layers, as you can see. One set is for the network from which it is receiving data. The other set is for the network to which it will go, it will send the data. Remember, these two networks can be completely different. This can be a simple LAN, this can be a WAN. So the requirements of the two different networks will be different. That's why the physical and data link layers will change. So at every intermediate router, we are going to have two sets. One set of physical and data link for the receiving packet network, the other set of physical and data link for the network where we are going to send the data. The network layer is one where this packetization and forwarding or routing happens. Okay. So at this network layer, it will check what is the destination. Bob is the destination, which is there in scientific books, and it will have an entry in its table telling it should go to router R4 as its next hop. So from R2, it will now forward the packet to router R4. R4 is the next hop for this network. Again, R4 is an intermediate router. It will have two sets of physical and data link. And what will happen? Again, the data coming from R2 will be taken from the physical layer to data link, where we know what all functions the data link do. So after all those functions, it will pass the packet to the network layer. The network layer will check the destination address, and it will know to reach this scientific books Bob, it has to forward it through this switched WAN to router R5. So it will forward it to this switched WAN, and from this switched WAN's switch. Yes? From a switch in this switched WAN, it will send it to router R5. And the same process repeats. R5 in its routing table will know that it should forward to R7, and R7 in its table here will know that it can reach Bob now directly, and it will forward the packet to Bob. So Bob is the receiver, and through the internet, which is a super network of many small networks, it will route itself and reach the destination correctly. So there are so many different processes involved when the packet travels like this, and all those things we will see with respect to layer 3 or the network layer. So you can see this is a simple representation. So in the summary of layer functions, I don't want to go to other layers. We'll just see here network layer to move packets from source to destination, or it is I can say this is a first or the lowermost layer, which is a complete source to destination layer. It will see that the packet which starts at the source will reach the destination correctly, and it helps to provide inter-networking. Okay, so let's just see what is this packetization. So the first job done by the network layer is packetizing, which means encapsulating the payload from which comes down from the transport layer into a network layer packet, and this is done at the sender site. So at the sending site, data flows down from transport layer. The network layer will take both the transport layer header and data into one packet, and it will forward it after adding the source and destination IP address to the data link layer. And data link layer will add its own header, which has the source and destination MAC address, trailer which has CRC and other things, and then forwards it to physical. And physical will send it on the actual network after doing so many things like encoding, then quantize, you can say sampling, quantizing, encoding, all that is done in the physical layer, and even modulation. So this network layer, we can say, works like the carrier in a post office, a normal post office, which when we pass on a complete sealed envelope, the carrier will carry it from one place to the other. So if you are sending it from Bangalore to Delhi, it will carry it from Bangalore to Delhi. It may be through air, through land, whatever. Okay. So the network layer is like a carrier. So first job of network layer, please remember, is packetizing. So breaking the data coming from the transport layer into manageable sizes known as packets. The data unit is usually called a packet. Routing and forwarding are the next two tasks of the network layer. So as we know, routing is finding a definite path from the source till the destination. What is the route to be taken if this packet should reach this particular destination IP address? Forwarding happens at each step. So at every hop, when it reaches one router, say it reaches this router, it should know that the next step in forwarding, it has received the data, say on link 1. I'll call this link, which is connected to Sky Research, as 1, the link here as 2. So it will know if I receive something from link 1, I should forward it to link 2. That is forwarding. For that forwarding also, we are going to make a table. And logical addressing or IP addressing is the main task of the network layer. So what happens in routing? So network layer is responsible for routing the packet from source to destination. I told you just now. So the physical network is a collection of networks, many LANs, WANs, everything. And routers or switches will interconnect at each step. So there will be more than a single route to reach the destination. So which route is the best? So which is the shortest route? Remember you did Dijkstra's in the lab, the shortest path algorithm. So you'll know which is the shortest route to be taking, and all that will be decided in the routing process. So we have multiple algorithms for routing, and using those algorithms we will find the best strategy to reach from the source to destination. Among all the possible routes, which is the best route? So how we do it? We do it with the help of some routing protocols which are already in use today. We'll be studying that in the next module, that is module 4. So in module 4, we'll be studying 3 different routing protocols which help us in finding the best possible route from a source to the destination. Next is forwarding. As I told you, forwarding is nothing but the action applied at each router when a packet arrives on one of its interfaces. So I was showing you in the example, if packet arrives from Sky Research Labs on interface 1 at router R2, it should know that it should forward, it will look at the destination address, which is in scientific books. So it should know if I should reach that, my next hop will be router R4, and it will forward it onto interface 2. So simple decision making table will be there at every router called as forwarding table. So this forwarding table will be slightly different from the routing table, but for now he gives almost the same name to both. Next, on receiving a packet from one of its attached networks, the router needs to find where it should forward the packet and send it on that outgoing interface. So if it is unicast routing, in the sense it should forward it only to one path. If it is multicast, it may need to send it to multiple attached networks, not a single network. So remember, I think you remember the difference between unicasting and multicasting. Yes? What is the difference? How many of you are there? Yes? Yes, Shashank? Yeah. One to many is multicasting, one to all is broadcasting. Unicasting, one to one is unicasting. Fine. Right. So, to make the decision of on when I receive a packet on this interface, say interface 1, I should forward it to interface 2 or 3. That decision is made with the help of the destination address, the destination's IP address, and also a label. We will use another additional parameter for forwarding, which is called as label. So that label will help us telling where I should forward. So I will forward it on interface, on some outgoing interface like this. You can see in this diagram, this router has 1, 2, 3 and 4 interfaces. It has 4 different paths. Each interface will be connected to a different network. So say for example, there is data coming on interface 1 and it has to reach the destination B. Let me say the destination is B. Now it will look into this forwarding table. What is the entry in the forwarding table? In the forwarding table, there is an entry showing if I should reach B. If B is my destination, I should send out the received packet on interface 2. The output interface is 2. So anything which is received on any interface, whether it is 1, 3 or 4, if it should reach the destination B, it should be sent out on the interface 2. This kind of entries will be there in the forwarding table, and automatically the router will refer to its forwarding table, and when it receives this data with destination as B, it will simply send it out on the interface 2. Okay, so this is a simple example. Now you just listen to this carefully. There are many other services like error control, congestion control, flow control, and security, but most of these are not implemented in the network layer. So we'll go through this fast. Error control is not implemented for the data. It is implemented only for the header. A simple reason why it is done in this way is because please remember, at every intermediate router there is a chance that data will be divided into smaller fragments, because based on the network where it should be passed on next. Suppose I have a network with larger packet size and it is going to a network which has a smaller packet size. Say for example from a wireless to wired network. In wireless network the packet size is high, 64,000, whereas in wired it's only 1.5 kb. So if we have to pass on data like this, that data should surely be divided into smaller manageable sizes or fragments. And when we do that, and if we have to do error checking, CRC computation and error checking for each fragment, it turns out to be cumbersome and very lengthy process. So what they did, they said we'll leave out this error control since the higher and lower layers will take care of that. Data link layer will also take care of error control. The uh, transport layer will also take care of error control. So they decided the network layer should be implemented as simply as possible, because there shouldn't be congestion in the in between routers. As data is traveling, it should be processed very fast and transmitted to the next hop. So remember, the data has to reach from source to destination in fractions of seconds or in fractions of milliseconds. Only then you'll have continuity, especially today where we are dealing with multimedia. If you are transmitting voice or video, you can't tolerate that delay, and that delay should not happen at the routers, in between routers, even if it is traveling very far, say from US to India or anywhere. So however far and however many networks it has to cross, all this should happen at a very high speed. So please remember, in network layer, error control is not implemented for data, but it is implemented for the header. We'll be studying about that. So all this, and flow control. All of you remember what is flow control, right? So a fast sender should not overwhelm or swamp a slow receiver. For example, your system and the printer. You shouldn't, the system will send data so fast that the printer can't print it as fast. So what it will do? It will buffer it. It will store all the sent data in a buffer and it will print at its own speed. That is flow control. And usually we saw how we can implement flow control when we do stop and wait protocol. You've done it in the lab also. By sending an acknowledgement from the receiver side to the sending side, the sender will know when to send the next byte or next packet of data. So here also flow control is not directly implemented in the network layer. It is taken care of in the transport layer. Okay, please remember. So upper layers will use the service of network layers. They will implement buffers and take care. Next, congestion control. Congestion will occur in every router. Remember, every router in the network will have some buffer size or some queue size. All the datagrams or packets coming to a router will be put into that queue. And whenever it has to process, whenever it processes one packet, the queue goes on getting incremented. In the sense, the last entered packet starts moving up. A general normal queue I'm talking about. So if that queue size is completed, so if the buffer size at the router or the queue is completely filled, any new packet which comes to that router can be dropped by the router. So usually we call it as a drop tail queue. Any new packet which comes after the queue at every router is filled, it can simply drop that new packet. That causes congestion. So when there is more number of packets, more than the queue size possible in the in-between routers, congestion happens. We say it is what? It is having some fixed capacity, and data it is receiving to process is more than its capacity. That's why there is congestion. So you remember we used a leaky bucket algorithm for congestion control. Anyway, this congestion control is also not done at the network layer completely, but a partial way of congestion control through these queues can be implemented. Okay, and especially when congestion happens and routers start dropping packets, all because of error and flow control implemented, all these packets will have to be duplicated and sent again. So more number of packets, more the congestion. At some point, the complete network may fail. Okay, that's about congestion control. Next is something known as quality of service. I told you this term comes into picture mainly for multimedia applications where you have voice, video and data, everything together. So real-time transmission of voice, audio, data, everything when we do it. So it becomes important to monitor some parameters like the data rate or throughput. We should be, when you're watching an online video streaming, remember, we don't want that buffering delay. We want it to play as fast as it comes. I don't want to have a delay in watching the movie, right? So throughput or data rate becomes important. Other than that, the quality in terms of delay, I should have very less delay, very high data rate or throughput, and a low jitter. Jitter is something known as inter-packet delay. You have studied about that. So even that should be less. So we have multiple parameters in QoS and it becomes important. So this internet has thrived, or it is sustaining even today by providing better and better quality to support newer applications. Better, every day we are getting new applications and it should be supported with proper quality. And yes, that is happening because at the internet we do it. But again, network layer we don't want to touch. We want to, I told you initially, only all these 3 or 4 points what we are discussing will not be implemented in the network layer, because we want this network layer to keep it as simple as possible so that it shouldn't have a longer processing delay. No congestion should be added. Next comes the security issue. This security was not important for us in the early days because then the networks were small. It was implemented only in some universities or colleges, some scientific labs for research. There were fewer systems on a network. So there was no security breaches, or nobody, unauthorized person would never try to access. But today that is not the case. Everybody uses internet and security is a main issue. Remember, even this Zoom app as we are using, there are chances that many people are trying to hack your data through this. Okay, so anything you enter on the Zoom app is not secure, we know that. But anyway, for our educational purposes, we don't have any secret content or private content, so it is fine even if they try to access these things. Anyway, so network layer had no security provision initially, but today we have added one more virtual layer in the network called as the IPsec layer. See here, it's known as the IP security or the IPsec layer. It has been added to the earlier existing network layer. Whichever network layer was there before, to that we have introduced or added this security layer, and by doing that we are able to increase the security level or protect our data more efficiently. Okay. So today we have something known as tunneling, encryption, many processes where we can protect the security. Encryption is done at a higher layer, but at the network layer, we add something called as IPsec. We'll not go into those details here, but if you're interested, you can read through. It's a very nice phenomenon known as tunneling, how they provide security at the network level. Okay. So please remember here, security we are going to add at the network layer through a virtual layer known as IPsec introduced into network. But this QoS, flow control, congestion control, error control, all these services we'll not bother to introduce in the network layer. Okay, we leave it to the higher layers to take care of that. The next thing is packet switching. So I told you the main function of the network layer is to divide data into packets or to create manageable size packets. So it's a type of switching which occurs. You have studied all the connecting devices in the previous classes. You are familiar with a hub, switch and router, right? So what is a router? Router is the device which is working in the network layer, and the main job of this router is to create a connection between an input port and a output port. If it is unicast, or a single input port and multiple output ports if it is multicast. Okay, so this job should be done by the router. And the two types of switching techniques we have here, circuit switching and packet switching. I think all of us remember what is circuit switching, right? Circuit switching was introduced in the first chapter itself, where we said a complete circuit should be established between the sender and the receiver. When you establish this circuit between sender and receiver, you will know. Okay. So prior to sending, so establish that circuit prior to sending, and then send the data in the same path. That is circuit switching. Whereas packet switching, every packet is considered independent, though it comes from the same message. The same message or the same flow, we break it into smaller sized packets. Each packet is considered independent of the other, and each one can take a different path. So I think I have a diagram which shows that. We call that as datagram approach, where every packet is treated independently. Remember, in network layer, we follow this packet switching. Yes. Yeah, the time. Are you able to see? Hello? Hello? Just let me know if you are able to hear and see. Okay, fine. So I think we have another 8 minutes left, after which we will log out and come back for another 10 or 15 minutes and try to finish this part. Anyway, you can log into the same ID and password. The datagram approach is followed. Datagram approach means it is nothing but packet switching. So in the network layer, every packet is treated as an independent entity, and if we want to get something similar to circuit switching in this network layer, we have a different way of attaining that, and we will be discussing that. So network layer is basically responsible for delivery of packets, and in the datagram approach, each packet is treated independently, and it may or may not travel in the same path, and it may reach the destination out of order. You can look at this diagram where it is clearly seen. See here, this is the sender. The network layer of the sender has created 4 packets, 1, 2, 3, 4, and it is passing it on to a network. You see here, there are multiple routers, 5 routers we have shown in this network. So you can see packet 1 takes this path from R1 to R4, then from R4 to R5, and then to the receiver destination. And packet 2 goes in this path, R1 to R2, then R5, and reach the destination. Whereas 3 and 4 follow this route, R1, R3, R5. So again, when 3 and 4 come here, 4 goes from R3 to R5 directly, whereas 3 goes from R3 to R4 and then from R4 to R5. So based on the situation at the router, like queue at the router, the protocol, the routing protocol used at the router, based on multiple parameters, every packet takes a different path. And this is known as a connectionless packet switch network, and our network layer basically does this. But with all this, you can see the packets can arrive out of order at the destination. So 2 has arrived first, then 4, then 3, then 1. But it is the job of the network layer to wait and accumulate all the packets and then reorder them correctly and pass it on to the higher layer or the transport layer. Okay. So it will wait till it receives everything, and only when it is in order, it will send it to the next higher layer. Now, this packet switched or datagram approach is the simple approach which is followed by the network layer everywhere. But if I want a situation similar to the circuit switching, I told you what is done in circuit switching. There is a route established beforehand from source to destination. So they will send some request packet and they'll get a reply packet, establish one route. Say they think R1, R4, R5 is the best route from this source to this destination. That route is established beforehand, and all the data packets which come 1, 2, 3, 4, everything will follow in the same path. It will not go through any other path in circuit switching. To get something similar with packet switch network, we use something called as a virtual circuit approach. As the name indicates, you get an approach similar to circuit switching, but it is virtual. It is not actually connected, but it is virtually connected. Okay. You can see how we do this. This is an interesting approach and a commonly asked question in the exam. So this virtual circuit approach is often either datagram approach or virtual circuit approach they ask. You should explain with diagrams. Here we have 3 steps and each one with a diagram, as I'll explain now. So remember, when there are multiple packets belonging to one message, all these packets will have some relationship between each other. And when we want all these packets to maintain that relationship, we want to send them in the single unique path. We don't want every packet to take a different route. We want everything to go through a single route. In that case, we have to establish a virtual connection between the source and destination. And that method is known as virtual circuit approach. So we have 3 phases for virtual circuit approach: the setup phase, the data transfer phase, and the teardown phase. So there will be 3 steps to establish this virtual connection between the source and destination. Let us see how this works. So in a virtual circuit, as I told you, at the end of all the 3 phases, this is what happens. a connection is established from this sender to receiver. They have established this connection based on some protocols, some routing protocol and conditions, and they decide R1 to R3 and then R4, and the receiver is the best path. So this path is established as a virtual circuit connecting the sender to receiver. And now every packet of this message, every packet coming from this message 1, 2, 3, 4, everything goes in the same path. So everything will arrive in order at the destination. There is no out of order packets. Okay. So this is a simple example of virtual circuit. Let us see how it works, how this is actually done practically. Okay. So first I told you there are 3 phases in establishing a virtual circuit. First is known as the setup phase. In a setup phase, the router creates an entry for a virtual circuit. So for example, source A needs to create a virtual circuit to destination B. Then it needs to exchange 2 types of packets between source and destination. One is the request packet. The other is the acknowledgement or the reply packet. We also call this acknowledgement packet as the reply packet. So 2 packets are sent. You see here how this forwarding happens in a virtual circuit network. There is a router with 4 ports or 4 interfaces, 1, 2, 3, 4. The same example what we had taken before. You can see this is a packet, and in this packet the source address, destination IP address and the data is there. To this data they will add a label known as a, it's a number, it's a simple number and it is called a label. Flow label they call it often. So they attach this label to the packet when it comes to an interface. So as soon as a packet like this reaches this interface 1 or port 1, it includes a label for this packet and it makes an entry in the forwarding table. And it will have an entry. It will know if I receive this and this is my destination, I should send it out on port 2 or interface 2. It will send out that. And at port 2, it has to make another label entry, but this will not exist before. It will happen later. I'll show you how this actually works. So I think in virtual circuit approach, the forwarding decision is based on a label given to the packet. So please remember, we attach a label to the packets coming from a single message. We call that single message as a single flow and the label which we attach as a flow label. So we'll see the 3 phases now. I'll just log out and log in. All of you please do the same. We'll have for another 10-15 minutes and wind up. Okay.